This is K8BYP, third video in the Balanced Modulator Mixer series. This one is looking at diode specs in detail on spec sheets. What I'm doing here is I'm going to use very high-tech, modern microwave diodes to replace the old school 1N270 germanium diodes used in the Balanced Modulator bridge and a Drake TR3. And my email, K8BYP underscores in between the characters at IEEE.org, not ARRL. Big difference. First, a little bit about graphs. We're going to look at the data sheet for a diode. The data sheets are tailored to the diode for the application for which it's intended. On the left, a graph, a linear graph. See the ticks on the X and Y are equal distance. And I just roughly drew in a curve that's supposed to represent a logarithmic response. It's a curve. And the same data is plotted on a graph with a log axis. Then the line that represents that log function is straight. So when looking at that graph, it's easy or easier, especially to print it out and put a straight edge against it to see where that line and that curve is straight and where it curves, where it's no longer logarithmic. Same function, different graph. To jump ahead a bit, after looking at a bunch of diodes, I'm looking at the Infineon BAT15 series, reverse series silicon Schottky RF diode pair. This is two diodes which are matched in a SOT23 surface mount package, very tiny. Feature list low inductance, a nanohenry and a half, which is nothing at HF. Low capacitance, a quarter of a picofarad, nothing. Here's where it gets interesting. About 3 millimeter by 2.5 millimeter or so. It's basically 1/10 of an inch wide, very small. Here's a schematic of the internal connection. That's the correct configuration for this diode bridge. A common anode cathode. Use 2 of these. It'll save making 2 connections over using 4 diodes. Ordering code, SOT23, 3 lead, etc., etc. Ratings, very important, reverse voltage. These diodes are very sensitive to voltage. 4 volts maximum reverse. 5 volts, they'll go boom. 110 milliamp, etc., etc. V sub BR, 4 volts reverse, where the current knees and starts going crazy at 10 microamp. Forward voltage, V sub F, about 1/4 volt. Very important. Forward voltage matching, 10 millivolt. And that is guaranteed 10 millivolt between the 2 diodes in that package. I don't know how it gets much better than that unless they're sorted by hand. This is the forward current versus forward voltage. Recall in the last video, I mentioned the regions on the graph where the device is nonlinear. We'll look at the y-axis here. This is a log graph. The lines start out space wide and get scrunched together, and then it repeats. That's logarithmic. And the graph being more or less straight till about 0.35 volts means that that response is pretty much logarithmic. The minimum turn-on voltage is about 0.65 volts. I'm sorry, 0.065, 65 millivolts. As in the previous video, anything below 65 millivolts won't turn the diode on. If we locate the noise in the modulation drive within that, then that will cut the noise out. There's a nonlinear range up till about 0.35 volts forward. That in itself doesn't really tell us much. Beyond that, I've seen from other diodes that that's essentially linear up there. But it's running away like crazy, probably not useful up there. If the maximum voltage on the logarithmic portion is about 0.35, two diodes in series is 0.7, divided by about 10 milliamps is about 70 ohms. That figure can be put in the circuit with the dividing resistors from the carrier balance pot to get an idea if the diode fits. Reverse voltage versus reverse current, pretty much linear until all hell breaks loose over 4 volts. The current goes crazy. So that graph will turn suddenly upward when a diode's destroyed. So a max of 4 volts reverse means that 2 in series can have a max of 8 volts peak on a half cycle RF, or 16 volts peak to peak before the diodes, 2 of them in series, are destroyed. The output from the carrier oscillator in the TR3 is about 2 volts or so way under that. Where this becomes interesting and difficult is noting that this appears to be a logarithmic response, nonlinear. But if we look at the math for modulation, we see it's a squared function. How's a modulation function, which is a square, going to map onto a log function? Well, it won't exactly. What's important here is that the modulation process, the mixing process, be the same in reverse as the detector and the receiver. If they both have the same function, then the modulation in theory might be transferred without distortion. If the old 1N270s did not have a log response and I put these diodes in, I will be changing the response of the mixer and modulator. I don't know exactly what's going to happen. My guess is it'll be a lot better than the gross distortion that I showed you in an earlier video because of the carrier leakage, because of the bad diodes. Assembling these diodes in a circuit, they're much too small just to make a diode bridge and wire in. See the exclamation mark? The top portion of the mark, that's roughly the size of this dual diode package, about roughly the same width. There are diodes, even in these series, and I've worked with diodes that will pretty much fit inside the period under the exclamation point. You talk about hard to solder. So make sure if you do this, you get at least SOT 23s. Since these are so small, and to eliminate the old resistors in the modulator circuit, I'm going to go to all surface mount, including the carrier balance pot. It's all going to be replaced. And that will greatly reduce stray capacitance in the circuit. And that should help be balanced by itself. There are 2 balances here. The diodes being matched among each other, and the sides of the transformer, especially with stray capacitance, being the same. And that's difficult because one side of the bridge tends to be towards ground. Using these ultra low capacitance parts and shrinking this down till there's essentially no stray capacitance will eliminate a lot of that, and this should come out really nicely. In the TR4, the diode bridge is inside the T14 can. In the TR3, the layout's very poor. There's a lot of lead length between the diode bridge and the transformer input, and that makes differences in stray capacitance on the sides of the transformer. So all that's going to be eliminated. So the little piece of circuit board about as big as your thumbnail will have 2 of those diodes, actually 2 pots, 3 resistors, and a coupling capacitor. And all that's going to be surface mount. So the thing will literally be the size of my thumbnail. And what's interesting about this is it's possible this has never been done before, to replace an old school set of diodes with microwave mixers. It may have never been done before. A 1960 radio with microwave diodes in it, who knows? Might be breaking new ground here. KBYP.